Hey, welcome! Have you ever stopped to wonder how a database can find one specific piece of information out of literally billions in the blink of an eye? Well, today, we're going to pull back the curtain on one of the most clever and essential data structures in all of computer science, the B-plus tree. Let's get right into it.
Really think about it for a second. You go to some huge online store, you type in running shoes, and bam, instantly you get a perfectly sorted list of results from a catalog that has millions, maybe even billions of items. How on earth does that happen so fast? It's not magic, I promise you. It's just some incredibly smart engineering designed to solve a really, really big problem.
And yeah, that's the fundamental problem, right? When you're dealing with a data set the size of a national library or a global retailer, how do you organize all that information so you can find what you need without it taking, a week? Let's look at some of the simpler early ideas to see why they just don't cut it.
So the first ideas people had were pretty straightforward. On one hand, you could just toss everything into what's called a heap file. This is basically like having a giant messy pile of papers on your desk. It's super fast to add a new paper, you just throw it on top. But finding a specific one? Good luck. You have to look through every single sheet. Then you have the opposite approach, a sorted file. Think of this like a dictionary. Finding a word is incredibly fast, right? But what if you need to add a new word? Well, you'd have to reprint the entire dictionary just to slot it in. So you can see the problem. Neither one is good for a system that needs to be fast for both finding and adding data.
And here's the thing you absolutely have to understand. The real villain in this whole story, the physical disk drive. Actually reading a piece of data from a spinning disk is thousands, sometimes millions, of times slower than reading it from your computer's memory, or RAM. So any system that wants to be fast has to be obsessed with one thing, minimizing the number of times it has to go to that slow disk. That's the whole game.
All right, so enter the hero of our story, the B-plus tree. It's a data structure that was specifically engineered to fight this exact problem, to conquer the slowness of disk drives.
So what is it? A B-plus tree is a self-balancing tree that keeps all your data sorted for super fast searching, but it also handles adding and removing data like a champ. The whole point, the entire reason it exists, is to achieve that one main goal we just talked about, keeping those slow disk reads to an absolute minimum.
So, how does it do that? Well, secret number one is that B-plus trees are built to be incredibly fat and short. Instead of being tall and skinny like you might imagine a tree, each little box or node in this tree can have hundreds, even thousands of children. This is called having a high fan-out. And why does that matter? Well, a shorter, fatter tree means you have to take way fewer steps to get from the very top, the root, down to the data you're looking for. Fewer steps means fewer disk reads. Simple as that.
The second big idea is this really clever separation of jobs. The upper levels of the tree, what we call the non-leaf nodes, they don't contain any actual data at all. They're just a roadmap. They're like a multi-level index full of signposts that just point you in the right direction. This is a huge difference from a regular B tree, by the way. In a B-plus tree, all the pointers that lead to your actual data records are stored only at the very bottom level, in what we call the leaf nodes.
And here's the secret sauce, the third rule that makes these trees so powerful. All of those leaf nodes at the very bottom are actually linked to each other, forming a kind of sorted list. This is what makes range queries ridiculously fast. So if you ask the database to find all products between $50 and $100, it just zips down a tree to find the $50 entry, and then it just follows the chain from one leaf to the next, grabbing everything until it hits 100. It's just so efficient.
Okay, but what happens when you need to add new data? The tree has to grow somehow, right? This is where the real genius of the B-plus tree shines. It knows how to rearrange itself on the fly to always stay perfectly balanced and efficient.
Let's walk through this together. Imagine we need to insert a new record with the key 9 into this tree. The process always starts at the top at the root node. Just like a search, we follow the signposts down the tree to figure out exactly where our new number 9 is supposed to go.
Okay, so we follow the path and we land right where the 9 should go. But, we've hit a snag. The node is already completely full. There's no room. Now, in that simple sorted file we talked about, this would be a disaster. But for the B-plus tree, this is just business as usual. It has a super elegant solution.
Instead of a total meltdown, it performs a quick, local operation called a node split. First, it just splits that full node into two brand new ones. Second, it divides all the keys, including our new one, evenly between those two new nodes. And third, this is the really clever part, it takes a copy of the new middle key and promotes it, sending it up to the parent node above. That promoted key now acts as a new signpost, pointing the way to the new node we just created.
And just like that, we're done. The tree got a little bit wider, but, and this is the critical part, its height didn't change at all. The whole structure is still perfectly balanced and just as fast as it was before. This split and promote dance is what lets a B+ tree handle millions of changes while staying lightning fast.
So, after all that clever work, the splitting, the promoting, the balancing, what do we actually get for it? What's the real-world performance payoff that makes this thing the king of modern databases? Get ready for this. This is a number that changes everything. Because B+ trees are so incredibly short and fat, you can typically find any single record in a database with billions of entries in just 3 or 4 disk reads. Not thousands, not millions, 3 or 4. That right there is a secret to making searches feel instantaneous. And this chart just puts it all in black and white. That heap file? Fast for inserts, but awful for everything else. The sorted file? Great for searching, but a total nightmare for updates. But the B+ tree index? Look at that. Very fast, and very fast. It gives you the best of all worlds. It's a true game changer.
And that's exactly why they are the absolute workhorse, the unsung hero behind pretty much every modern database you've ever used, from your bank to your favorite online shop. They just offer this perfect, masterful balance between speed and flexibility. Now, we've covered the theory, but how do people actually use this in the real world? Because just having a B+ tree isn't the end of the story. You still have to tune the engine for maximum performance.
Well, one of the biggest decisions is choosing between what's called an unclustered and a clustered index. Think of an unclustered index like the index at the back of a textbook. It's a separate little structure that tells you what page number to go to, but the information itself could be anywhere in the book. A clustered index, on the other hand, is the textbook. The data itself is physically stored on the disk in the exact sorted order of the tree. That's why a table can only have one clustered index. You can only physically sort your data one way.
So, which one is better? The answer, like with so many things in engineering, is it depends. It depends completely on your workload. If you're constantly searching for ranges of data, like give me all the sales from last month, a clustered index will give you a massive performance boost. But if you're mostly doing lookups on individual records using lots of different criteria, then having several unclustered indexes might be the way to go. It's all about strategy.
The B+ tree is just a perfect example of a beautiful, elegant solution to a really tough problem. It kind of makes you wonder, right? What other brilliant, hidden algorithms are working tirelessly behind the scenes right now, making our digital world feel so seamless and fast? Thanks so much for joining me on this deep dive.